Hello everyone, today we'll present to you some advances in deep reinforcement learning approach applied to video games. In general, game artificial intelligence is concerned with sensing and decision-making in virtual worlds. There are some critical difficulties and possible solutions associated with these components. The game's state space is usually very wide and it's difficult to learn correct policies for make decisions in a dynamic and uncertain environment. Data-driven methods such as supervised learning and deep reinforcement learning are viable solutions for this problem. In this work, we will demonstrate the effectiveness of deep reinforcement learning on the visually complex modern video game, focusing mainly on the low-dimensional observation filter for preprocessing the input image of each time step. Our proposed approach consists of training our deep network agent using our image filter. Our system definition can be seen in Figure 1 present on the screen. The neural network architecture used to train and other significant steps of our DKN agent structure can be seen in Figure 2 present on the screen. We use a classical CNN architecture with 3 layers of convolution and layers of batch normalization between them. The activation function was applied to the batch normalization output, and the outputs from the linear layers are the 3 discrete actions that will be sent to be performed in the environment. The core idea of reducing the extra image information present in the environment observation revolves around cropping and binary filtering. The image processing pipeline performed in this work can be seen in Figure 3 present on the screen. With the BGR screen saved, the image was cropped, removing almost 50% of the upper pixels, 20% of the lower pixels, and 20% of the left and right pixels. Then a color to grayscale filter was applied. After that, the triangle threshold function was applied to transform the image to binary. Finally, we resized the final image to 160 times 90 pixels using area interpolation. The use of interpolation resizes before the CNN ensures the correct input shape will be sent to the CNN, independent of the monitor window's size that the video game is being played at. If the car surpasses the first obstacle, a positive reward of 1 is given. If the car collides with an obstacle, a neutral reward of 0 is granted to the step. Finishing the episode at this time. In our environment, the vehicle was set to always start at the same initial checkpoint. The agent had also to navigate through the environment, while avoid the obstacles in order to maximize the reward, reaching the next goal without a collision. Since the map never changed, the navigation was basically a memorization problem. The performance was measured by moving average of 25 training episodes. This is shown in Figure 4 present on the screen. To test the robustness of our approach, we input salt and pepper noise in the input images before the observation preprocessing. For this task, we use 4 samples of salt and pepper noise, 0.4%, 1%, 10%, and 25%. The results can be seen in Figure 5 present on the screen. For low noise inputs, the results kept almost the same average, but for the higher noise inputs, 10% and 25%, the moving average of the reward is decreased drastically. Thanks for the attention, and on the screen is displayed my email, the GitHub repository, and the YouTube video reference to this work.